Okay, so yeah, so we're live now. So can you share your screen there?
Yeah.
Okay, there we go. Okay, so welcome back everybody to the fourth day of this workshop. So for the first talk today, this is a quite unique talk because it's going to be jointly given by two people, by Leon Bungert and by Tim Royth from Frederick Alexander University, Erlangen-Nuremberg. And they're going to talk to us about L-infinity variational problems on graphs, applications, and continuum limits.
Yeah, thank you very much, Jeff, for the nice introduction. And thanks for giving us the opportunity to give this talk at this interesting workshop, especially since it's a joint talk. It's kind of unusual, but we're thankful that we can do it that way. Okay, so before I start with my talk, I would like to thank our collaborators. First of all, we have Martin Burger from the University of Erlangen, then Daniel Tenbrink from the University of Erlangen, and Yuri Korolev from the University of Cambridge, who all contributed to what we will present today. Okay, so this is the outline of the talk. We will start with a short motivation on the kind of L-infinity variational problems that we would like to study. And then in the first main part of the talk, I will speak about one specific variational problem, both in the continuum setting and in the graph setting. And then I will also study applications. And then in the second main part of the talk, Tim will speak about continuum limits of the problems that I introduced before. And he will also show applications to Lipschitz learning and ground states, and the computation of ground states. Okay, so let's get started. A very popular task nowadays in data science and machine learning is so-called semi-supervised learning, where one is given a set of data points, x1 to xn, which live in some space, let's say r to the d. And additionally, we assume to have labels g of xi to g of xn, where typically capital N is much smaller than n, which means that we only have a small amount of labeled data and the rest of the data is unlabeled. And in this semi-supervised learning setting, we are looking for a function u from the whole, from all data points to r, which fulfills the constraints on these labeled data points. So we basically seek for an extension of the labeled data to the unlabeled data. All right, and just to give you a first example, this image here shows a graph of MNIST images. So I believe here we have the numbers 0, 1, and 6. And then in a semi-supervised learning approach, we could manually label 3 of these numbers. Let's say we label a 0 and a 6 and a 1. And then we would like to diffuse these labels to the rest of the data points in order to get a classification. And one can solve this and get a nice segmentation of this graph into 3 subgroups corresponding to 3 different digits. Okay, so mathematically, this is often modeled as a graph-based problem, because one should say that the semi-supervised learning problem alone is of course not well posed, because there are several different versions of extensions that one can look for. But in order to find a unique extension, let's say, one typically has a smoothness assumption on this labeling function u. And one can, for instance, look at P-Laplacian learning on graphs, where one uses the data points x1 to xn in order to design a weighted graph with these vertices, which also comes with a weight function w. And then on this weighted graph, one minimizes this discrete functional here, which is basically the analog of a p-Dirichlet energy, and which makes sure that the labeling function is kind of smooth. And of course, this minimization is subject to the constraints of the labeled data. And as I already indicated, there's also a continuum problem associated to this graph P-Laplacian learning problem, which takes this form. Here we look for a function u in W1P, which minimizes the p-Dirichlet energy subject to the labeling constraints. And it's quite obvious that it's also interesting to study the relation between these two problems. And this is typically referred to as continuum limits. So if we send the number of vertices in this graph to infinity, we would like to have that this problem behaves similar to this continuum problem. And indeed, this was done by Nicolas Garcia-Trios, Dejan Slepčev, and Matt Thorpe in 2 papers, where they studied the continuum limit of this graph-based model to the continuum model using the tools of gamma convergence of these 2 functionals here. Okay. However, there's a problem with this P-Laplacian learning, namely that it's only well posed if the parameter P is larger than the dimension of the data space, let's say. And basically the reason for that is that in this case, we have a Sobolev embedding of W1P into a space of continuous functions. And only then these pointwise constraints make sense. However, if we are interested in very high dimensional data, which corresponds to sending d to infinity, basically, the data dimension, we are basically forced to consider the case p equal to infinity if we want to have a well-posed semi-supervised learning problem. In this case, p equal to infinity is typically referred to as Lipschitz learning. And naively, one could just send p to infinity in the 2 problems that I've showed before, which gives this graph Lipschitz learning problem where one minimizes the maximal local Lipschitz constant on the graph subject to the constraints. And the continuum problem here would be the minimization of the infinity norm of the gradient of a function u subject to the constraints. However, both of these problems have a disadvantage, namely they don't have a unique solution. And this can be visualized quite easily in a 1-dimensional setting. So let's say that we have 4 labeled data points corresponding to these red dots here, and we would like to find an extension. Then all of these 3 curves, which are drawn here, they solve this Lipschitz learning problem. However, they differ quite a lot in this region where there is no labeled data point at all. And the reason is that if you only care for the global Lipschitz constant, then you can change your function in the regions where the Lipschitz constant can be small, and you get a huge set of solutions. And this led to the study of absolute minimizers of these functionals here, which are, so to say, minimal in a local sense. And this can also be rewritten as being infinity harmonic, where infinity harmonic means that the functions solve an infinity Laplacian equation. So on a graph, this would be that the graph infinity Laplacian of u is equal to 0, where the graph infinity Laplacian is just given by this formula, and it's basically an average of the smallest and the biggest local slope, let's say. And in the continuum, there's also a infinity Laplacian, which is defined like this. However, here the intuition is not quite clear. Therefore, it's easier to study the graph problem if one wants to understand what's actually happening. So both of these problems admit a unique solution, and the solution of these problems also solves the Lipschitz learning problem, which is good news, of course. And also here, a continuum limit was studied by Jeff Calder in a recent paper. However, here he didn't use gamma convergence because there is no minimization of a functional involved, but he used viscosity solutions, which is the right solution concept for this continuum equation, in fact. However, in this talk, we would like to argue that it's still interesting to study these basic Lipschitz learning problems, which do not necessarily have a unique solution, but still is interesting to study a continuum limit there because it also has applications to other fields, as we will see. And this is what Tim will speak about in the second part of this talk, where he will prove gamma convergence of these discrete infinity functionals to the continuum one here. However, an infinity type functionals, like the infinity norm of the gradient, also appear in other problems, namely in nonlinear eigenvalue problems. Okay, so for those who are familiar with this topic, the minimization of such a Rayleigh quotient here of a p norm of a gradient over a p norm is equivalent to this p Laplacian eigenvalue problem. This can be just seen by writing down the Euler-Lagrange equations. Then sending p to infinity leads to the minimization of this infinity Rayleigh quotient here, and this PDE here converges to this PDE, which should be understood in the viscosity sense. However, sending p to infinity, you lose the equivalence that the minimization of this quotient is equivalent to the solution of this equation. And in fact, solutions to this eigenvalue equation they have very mysterious properties and are hard to study, which was mostly done by Uutinen and Lindqvist 20 years ago approximately. But very recently, my co-authors and I were able to derive a discretization on graphs for this eigenvalue equation and prove convergence to the viscosity solution of this equation. However, in this talk, I will not speak about this in detail. I would just like to mention that you can also send p to infinity in a different way. Namely, you can send it to infinity in the denominator first, and then you will get, so to say, p harmonic potentials here on the right-hand side. And then you can send p to infinity also in the numerator, and then you will get infinity harmonic potentials. This was studied in this paper. And what I will talk about today is sending p to infinity in the numerator first, which will give us this minimization problem here, and whose PDE counterpart turns out to be this differential inclusion here, or this sub-differential inclusion. And what we showed in a recent paper was that the solutions of these problems are distance functions. And then sending p to infinity, this doesn't change at all. So basically for every p, we get a distance function as the minimizer of this quotient, which is a new interpretation. So the setup for the first part of the talk is the following. We consider an open domain omega in Rd. And then in the closure of omega, we have some set curly O, which is the constraint set. If you want to think of supervised learning, that's the set where we want to prescribe values. And then we define a functional E on L2 of omega, which is the infinity norm of the gradient, if the function U is it's in W1 infinity, so basically Lipschitz continuous, and it is 0 on the constraint set, and otherwise we set it equal to infinity. And the reason that we define the functional on L2 is just that we want to define, we want to study its L2 gradient flow later. All right, and we've already talked about the applications. It's Lipschitz learning, infinity Laplacian equations, Lipschitz extensions, and so on. And in this first part of the talk, I would like to tell you more about the ground states of this functional, so the quotient minimizers that we've seen on the previous slide, then its gradient flow, and also its discretization on graphs. And what we don't want to do here is we don't want to approximate this functional with finite p functions like this, because this, first of all, it's not elegant. You need rather technical tools for that, and you don't gain so much insight. So we stick to the p equal to infinity case here. All right, so let's get started with the analysis of this functional in the continuum. And first of all, I promised that we will speak about ground states, which were defined as minimizers of such a Rayleigh type quotient, where here the p is between 1 and infinity, infinity excluded. And the theorem that we were able to prove is that up to scaling, so to say, the unique minimizer of this quotient here is given by the geodesic distance function, which is just the minimum of the geodesic distance of a point x to a point y, where y is in the constraint set. Okay, and if the constraint set curly O equals the boundary of omega, or if omega is a convex set, then one can also replace this geodesic distance here by the standard Euclidean distance. Okay, let me just mention that for p equal to infinity, the distance function is also a minimizer, but it's not the unique minimizer, and this doesn't make it so interesting. Okay, then the second thing is, if we want to derive a numerical scheme for the computation of this first eigenfunction of this ground state, we need non-negativity of the eigenfunction that we would like to compute. This is a well-known property also in Perron-Frobenius theory and so on. If you want to derive an algorithm which provably converges to an eigenvector or an eigenfunction, you need to have some notion of non-negativity. And so the question is, are there other non-negative eigenfunctions apart from the distance function? And the answer is, luckily, no. Any non-negative function in L2, which is an eigenfunction of our functional in the sense that it fulfills this subdifferential inclusion here, coincides with a multiple of the distance function. And this is very useful because from this we can derive the following corollary. Let's say we study the gradient flow of the functional E. The gradient flow is just this subdifferential inclusion here, initialized by some datum f, and we assume that f is non-negative. then if you rescale the solution of this gradient flow u by the energy itself, this will converge to the distance function as t goes to infinity. And the convergence takes place in L2 a priori, but in fact it also takes place in L infinity. So it's a uniform convergence. And this result is not that obvious. Actually, it follows from abstract results from a previous paper where we proved a similar property for abstract gradient flows, but applying it to this situation, we get a nice algorithm, so to say, to compute this geodesic distance function on an arbitrary domain. Okay, but in fact, more is true. One can also derive an explicit solution of this gradient flow. And just for, in order to have an easier notation, we assume that the constraint set curly O is given by the boundary of omega. And yeah, we shortcut the distance function to the boundary by d of x. And then we can define a number r, which is just the maximal value of the distance function. And the maximal value of the distance function to the boundary of a domain is typically referred to as the in radius of omega, because it's the radius of the largest ball which fits inside, which fits into the domain omega. So this is the number r. And then we define sets omega tau, which are defined as the inner parallel sets with distance tau. So here you can see on this image on the right, here the red set is omega tau because it has distance at least tau to the boundary of omega. Okay, so we need these two quantities here. And then what we were able to prove is the following. Let's say we study the gradient flow again, and we take an initial datum f, which is a constant function. So it's constantly equal to r for all x in omega. Then the gradient flow has an explicit solution given by this pointwise minimum here of the distance function divided by some function g of t and the constant r, which we initialize the gradient flow with. And this function g, which appears here, is basically the velocity which drives the initialization, the constant initialization to the distance function. And in order to illustrate that a little bit, I have this small picture here. So let's say that omega is just an interval and we initialize with a constant function. Then what the gradient flow will do is it will decrease the maximal slope until you finally arrive at the distance function. And this evolution is analytically available and it's given by this expression here. And of course, I have to tell you how to compute this function g of t. And this is done by solving an ordinary differential equation. So g of t has to solve the equation g squared divided by a function I of g should be equal to the derivative of g. And here this function I, which appears in this ODE right hand side, is given by the integral of the distance function over these small strips around the boundary of omega, which have width tau. Okay, and if you solve this ODE, then the solution of this ODE will give you a solution of the gradient flow as we've seen before. And just to give you some intuition, let's say that omega is a convex set, then you can estimate that this integral over this green strip here scales like tau to the power of 3, which for the ODE solution here means that the g of t is approximately the square root for small times. And in general, for general sets, this scales at least as tau to the power of 3, which means that g of t is asymptotically smaller or equal than a square root. So this ODE is well posed in any case, and this, so to say, gives us the velocity with which the solution converges to the distance function, which is quite nice. And then I would like to transfer these results also to the discretization of this functional on graphs. So as in the beginning, we consider a finite weighted graph G, which consists of vertices omega and of a weight function W. And again, we have a subset of vertices curly O, which corresponds to the constraint set as we've seen before. And then we define the discrete version of this functional E of u as, so to say, the largest local slope which appears in the graph. So this is basically a partial derivative on the graph weighted by the weight function. And yeah, so this is the largest slope that occurs. And the functional is defined on all functions u in this space H of omega O, which is nothing but the space of graph functions which are 0 on the constraint set. Okay, so this is the same setting as we had it in the continuum, and I would just like to mention that we equip this space of graph functions with this inner product here. And then what we can show is the same as we could show in the continuum, namely that the ground states of this discrete functional, so the minimizers of this quotient here, are just given by the geodesic distance functions on the graph. So where the graph distance d of x and y is given by this expression here. So you basically take the minimum over all paths from x to y, and you sum up the reciprocal weights along this path, and this gives you the graph distance. Okay, so this is precisely the same result as in the continuum. And also for the gradient flow, we can derive the same properties basically. So if we study this gradient flow of the discrete functional here, then we can also derive an explicit solution of this form here, where again this function g of t solves an ODE, which has precisely the same form, only that this integral functional I of tau now becomes a sum, of course, because we're on the graph, a sum of the distance function squared over all the nodes which are tau close to the constraint set, let's say. Okay, now I would like to show you some applications of this distance function business on graphs. And first of all, what you can do is you can take a simple grid graph, for instance, this grid graph, which has the shape of the United Kingdom. And then as a constraint set omega, you just use the boundary of the graph. And then you can very easily compute the distance function of this graph using the gradient flow approach that I've showed you before. And then you can compute which cities in England are farthest from the open sea. And a bit more interesting is the following example. Here we take this image of poppy seeds, and on this image we construct a graph by connecting two vertices with an edge if their local patches around the vertices look similar. Okay, so this is a non-local graph which is behind this image with a non-local patch distance, and then the constraint set is this single pixel that you might or might not be able to see. It's a pixel within this red poppy seed here. And if we compute the distance function to this pixel, then we basically compute all the regions in this image which looks similar, or whose patches look similar as the patch around this constraint set. And then we will get something like this. So of course, all the poppy seeds look similar, so they have a very small distance, which is indicated by the blue color. And then the green lawn here, the grass, has a larger distance, so it's red. Okay, and then you can also do this on a discretized manifold, for instance. So here we have this two-dimensional manifold which is embedded in 3D, and the constraint set is just the single node up there. And then using the gradient flow on this graph, we can compute the geodesic distance function with respect to this single node here. And then we can also iteratively refine the manifold, get a final resolution. And in the end, we get as a continuum limit, so to say, the continuous distance function, the geodesic distance function on this manifold. And this continuum limit, which I've just shown numerically, paves the way to the second part of the talk, which is given by Tim. And he will speak about, or he will prove, in fact, this continuum limit that I've just shown.
Thank you very much. I'm happy to give the second part of this kind of unusual shared talk. Okay, so as already introduced by Leon, I'm going to talk about continuum limits. Just to set the scene, what I'm talking about is I have a sequence xi in omega, and again I use the notation curly O for the set of labeled vertices, and then what I'm looking at is this set omega n, which kind of cuts off this point xi. Just as a reminder, in the usual random geometric graph setting, these xi would be distributed with respect to a probability measure. Right now, I'm in a deterministic setting. I will explain later why this makes sense in my case. Okay, now what are continuum limits? We have already seen this in other talks this week. I'm interested in the behavior of the graph functionals or respectively operators for n tends to infinity. Okay. So far I have the vertices. Let's talk about the weights and the kernel function. This is also standard. What I'm doing is I use a kernel function to define the weights. So I put in here the Euclidean distance of two vertices. And then I have an additional scaling parameter here. Just some pictures from typical kernel functions. Here, a Gaussian kernel and a characteristic function, which is a discontinuous kernel. So the assumptions are not that strict. We just assume that it's positive and continuous around 0, which makes sense, of course. It should be monotonously decreasing. And now this assumption here is a little bit restrictive. We assume that the kernel has compact support. In fact, it avoids many technicalities, but it's actually not necessary for the analysis, but it will make our lives easier. Okay, and as I already said, the scaling here, of course, is introduced to give significant weight to vertices that are close together. So the idea is here that in the limit, we want to localize this kind of non-local structure that we have in the discrete setting, for which we want to weight vertices that are close together. So in particular, the scaling parameter is a null sequence. Just some pictures, very easy. So we have a graph here. This is the support of the kernel, and then as the number of vertices is increasing, the support gets smaller. And just for intuition, what can happen is if the support of this kernel is too small, then our graph becomes disconnected, or even we get vertices that aren't connected at all to the labeled set, to the labeled set. And this is something that we want to avoid. So intuitively, we want to control the scaling parameter so that it doesn't tend to 0 too fast. And as I said, we are in a deterministic setting. So what we are doing is we introduce this parameter, Rn here, which measures the maximal distance of a point in the continuum domain to the discrete vertex set. So if we look at this picture, here in green, this is our set omega, and then we measure the distance to the nearest vertex of a point x here, and over all these distances, we take the maximum or the supremum. Okay. Now let's look at the related works. Leon already mentioned this paper by Jeff Calder, which looks at the consistency of Lipschitz learning, which is exactly in the setting that I talked about before. Okay, so he works on the flat torus, and he looks at the graph infinity Laplacian. We've seen this before. Now I have chosen the weights here as my kernel function, and we want to see convergence towards the continuum infinity Laplacian, already introduced by Leon. And we've seen this before. So the problem on the graph is formulated similar than in the continuum setting. And of course, here we have to use viscosity solutions, which is the right concept for the infinity Laplacian. Okay, so this was proven by Jeff Calder in the paper I mentioned before. In fact, as I said, we have to control the scaling parameter here, and so to say, the control he identified was that this maximal distance Rn fulfills this property. And if this is fulfilled, then we know that Un, the discrete infinity harmonic functions, converge uniformly towards the unique viscosity solution. Okay, this is the main theorem of proven by Jeff Calder in this recent paper. And what I was motivated by especially was this paper by Slapchev and Thorpe, who look at variational methods for the P Laplacian. As Leon introduced before, what I want to do is to prove similar results for a variational formulation of the Lipschitz learning task. Okay, so let's look at the functional of this paper here. They have this energy functional, which is kind of the Dirichlet energy on the graph. And now the constraints can be incorporated by using the standard trick that we just set the functional to infinity if the function doesn't meet the constraint. So this is standard. And the main point here is that these vertices are distributed now with respect to a probability measure. So this is not a deterministic setting anymore. And it is in fact important because the continuums functional, which they prove gamma convergence for, or the convergence result, has the following form. And if we look at it, we can kind of see where it comes from. So this gradient u to the power of p comes from this term here and the scaling to the power of p, which of course approximates something like a difference quotient. So that produces the gradient. And then these rho, the density here, is coming from the vertices xi, which are distributed accordingly to this probability measure. Okay, we will see later on why this is not the case for the respective infinity functional. Okay, and what Leon also mentioned, that of course we can only have pointwise constraints if p is greater than d because of this embedding. Otherwise, we cannot enforce these pointwise constraints as we see here. So the result that they've proven is of course also dependent on the scaling. So the scaling now is of course, now that we're not in a deterministic setting anymore, we get the following bound. And if you work with random geometric graphs, this term is familiar because this is associated to the connectivity threshold of a graph. And this is the lower bound for the scaling Sn. And in fact, in this case, you do not only need a lower bound, but also an upper bound. So Sn should also go to 0 sufficiently fast, which is which you can find in this assumption that n times Sn to the power of p tends to 0. And now Leon said before, we don't care about the limit p equal to infinity, but just for intuition, if we would do the same for p goes to infinity, we observe that this isn't a problem anymore, and that we can always ensure this if Sn is a null sequence. Okay, now the result is similar. If we have a sequence of minimizers for this functional, for this energy functional that I talked before, then almost surely now we have a subsequence that converges locally uniformly to the constraint functional. Okay, so this is the main theorem of paper by Lipschitz and Trias, and the proof here employs gamma convergence, and it uses optimal transport theory, which also is not necessary for my case in the infinity case. This is why I won't go into this in detail, but I will refer to this paper by this is by Trias and Lipschitz, which was the original paper on the continuum limit of total variation on point clouds, and there they introduced the necessary optimal transport tools that also allowed to prove this convergence result here. Okay, so much for the related work. Now let's look at the continuum limit of Lipschitz learning. So the functional that I now want to look at has the following form, and we observe that this is in fact the pointwise limit of the p energy that we've seen before. Like if we look at it again, this is the functional for finite p, and if we send p to infinity here, of course, take it to the power of 1 over p and then send p to infinity, this is the functional we arrive at. Okay, so this is the one I will work with, and we also notice that this is the functional that appeared in the Lipschitz learning task that Leon introduced before. Okay, and now the respective continuum functional has this form. It's just the supremum norm of the gradient, and we see already that incorporating something like the a measure here in front would not make sense, or would because the essential supremum so to say only respects null sets. It doesn't really care about the weight given by a measure. So we only have to we only work on the support of a measure, which is why it also makes sense to look at the whole theory in a deterministic setting. Okay, and what we want to do, as said, we want to establish a gamma convergence result. Okay. Now, quickly, we introduce gamma convergence. I guess this is not really necessary, but we have a sequence of functionals Fn, and we say that it's gamma convergence if the following two inequalities hold. We have for each sequence we have this lim_inf inequality, and then for every x in a metric space, we know that there exists a sequence for which this lim_sub inequality holds. So if you want to prove the results, these are the two inequalities we have to look at. Okay, how are we going to do it? The structure of the proof is similar to the one by Slapchev and Thorpe, and respectively by Trios. We introduce first a non-local auxiliary functional on the continuum. So what this is a functional that acts on L∞ in the continuum, but has this non-local structure where we compare 2 points x and y within the support of this kernel. And then what we show is that for sequence Sn, for null sequence Sn, then we have gamma convergence of these functionals towards the continuum functional. Then we have a scalar here. This is not that important actually. This scalar here is just bears some information about the kernel. Yeah, it's not that important, but it appears in the convergence. Okay, how? Let's quickly introduce the ideas of the proof. So for the lim_sub inequality, which is the easier one in this case, we just use Rademacher's theorem, which tells us that every Lipschitz function is differentiable almost everywhere, because working in W1 infinity means that we deal with Lipschitz functions. And this inequality, which, yeah, if you've ever seen the proof for Sobolev embedding theorem, then this is familiar. So using the Rademacher theorem and this inequality, we can show that we actually have pointwise convergence or strong convergence of these non-local functionals, which is not very surprising for Lipschitz function u here. Okay, so this is the easy part. For the lim_inf inequality, what we do is we take a sequence in L∞, and of course assume that the functional, that the lim_inf here is finite. This is the only relevant case. And from this assumption that the lim_inf here is finite, we want to infer that the limit function in L∞ is Lipschitz. And how we do that is we look at this difference quotients which appear in this functional and show that they converge weak star to the gradient of u times h, which appears in the difference quotient here. So we have weak star convergence, and then using weak star lower semi-continuity of the infinity norm, we arrive at the inequality. So these are the basic ingredients for the proof. Okay, and now how do we? This all is on the continuums level. The question now is, how do we do this for the discrete? How do we go from the discrete setting to the continuum setting? Okay, what we will do is we simply associate discrete functions, we associate them with piecewise constant L-infinity functions, which is also standard trick. So how we do this? We consider this map Pn, which goes from omega to omega n. This is the closest point projection. So for each x in the set omega, we choose, so to say, the nearest vertex. This is what this map is doing. Okay, and now we introduce the set an, big An. Now this is a bit technical, but what this is just the set of all L-infinity functions that are piecewise constant on this Voronoi tessellation, which is induced by this map Pn. Okay, and with that we can extend our discrete functional onto L-infinity by just adding the characteristic function, which yields the value in infinity whenever u is not piecewise constant. Okay, so this is just a technicality, and what we see then that for such a un which is piecewise constant, we have that the discrete functional can be written in the following form. So this is now this discrete functional, and if we plug it in, we get the essential supremum over the whole domain omega by this transformation Pn. And here we get the function, but the problem is that in the kernel function we have a difference Pn of x minus Pn of y, and this was also the problem in the paper by Lipschitz and Trios. They had to do a similar estimate, and namely we want to estimate this kernel by the kernel where we plug in the actual Euclidean distance of x minus y, and at the cost of probably having another scaling. How do we do this? So the interesting part, let's say eta is the characteristic function. So the only problem is if this distance is greater or is not inside the support. So this produces a zero. This produces a zero exactly if Pn of x minus Pn of y is greater than the scaling Sn, which means that the vertices are too far away. In this situation, we can use this triangle inequality here, or the reverse triangle inequality, to see that x minus y is greater than Pn of x minus Pn of y minus 2 times identity minus Pn in the infinity norm. This is just the reverse triangle inequality. And then we know that by assumption, this is greater than the scaling Sn. And this part actually, if we remember, is our value Rn, by which we want to control the graph. Now, we define this as our new scaling. And what we have to ensure is that at first, this part is positive, so that in fact it is a scaling. And what we also want to do, of course, we can, by this estimate, we can then write this part here as the non-local auxiliary functional. But as we have 1 over Sn here and 1 over Sn tilde and the non-local auxiliary functional, we get this in the additional term. So we have to ensure that this additional term converges to 1, from which we obtain the bound that Rn divided by Sn tends to 0. So this computation should motivate where my bound comes from. And then in fact what I have is that if this holds, then I have that the constraint discrete functional converges to the continuums functional in L infinity. Okay, and convergence of minimizers, how do we do that? Well, we know that if we have a compact functional, which just means that if for bounded sequence, which additionally fulfills that the supremum is bounded, it implies that Xn is relatively compact. Then we want to call a sequence of functions compact. And it is well known that for such functionals, we have convergence, or gamma convergence implies convergence of minimizers. So that is the next step, so to say. We have that under this assumption that in fact my functional, the sequence of functions here is also a compact sequence of functionals, and therefore we have that every sequence of minimizers has a cluster point that is a minimizer. This is, so to say, the main result that I've proven. Okay, and if you apply this to ground states that we've seen before from by Leon, this is just a repetition before, we get the following result that for a sequence of ground states here, which are distance functions, they do in fact have also a cluster point, which is the distance function in the continuum setting. Okay, here just the ingredients for the proof, but I guess I'm unfortunately out of time. So yeah, thank you for your attention. Any questions?
Okay, thanks for the really interesting talk. If you have questions from the audience, please raise your hand or type the question into the chat box and I can ask the question. But maybe I'll start with asking a couple of questions. So in the last part of the talk with the gamma convergence, right? There's nothing about absolutely minimal minimizers. And so I'm wondering if, so here you can show them with the gamma convergence that if I have a sequence of minimizers, then they converge to a minimizer of the limit functional. But can you say anything if the sequence of minimizers are absolutely minimal minimizers in the graph? They have to converge to the absolutely minimal minimizer.
Exactly. So that's exactly the point what I cannot do right now. So of course, what I know is if I take a sequence of absolutely minimizing functions on the graph, I know that they solve the Lipschitz learning task in infinity, or the minimizing problem in the continuum, but I do not know that it is the unique absolutely minimizer in the continuum. And the interesting point for me is because if I compare it to your result, my scaling assumption is a bit weaker, and yes, I assume that it's actually this difference maybe that will then provide the possibility that also a sequence of absolutely minimizing function on the graph converge to something else.
Yeah, I think it should be possible to prove this. So we can talk later maybe in the breakout room. Okay. I see Nicholas has his hand up, so let me unmute Nicholas to let him ask a question too. Here we go.
Hi, Leon and team. Thank you for your nice talk. I guess I have two questions. So one is related to so if you use this, you know, the P's that emerge there to compute distances, how would this compare on a graph setting? How would this compare to, say, Dijkstra's algorithm? I mean, you know, would you expect that if you're computing maybe the distance to not just one point, but maybe more, you know, a set of more points, that this could have any advantage in that setting? That's one question. And then the second question is, so related to this point that you were making about the density being lost in the limit. So if one wanted to still recover some information on the density, I mean, how would you do that? Especially in terms of, you know, again, this problem of computing distances. So perhaps one is interested in the limit in computing a distance that takes into account not just the geometry of the support, but also kind of like weights things depending on distance, so that somehow regions of, you know, small density, you know, the metric that you get there should not matter too much. So have you thought about how you would be able to do that?
Yeah, so I will go ahead with the first question, which was related to the distance function computation. So, well, I haven't thought about Dijkstra, but I've thought about fast marching, because what our algorithm does is very similar to what fast marching does. It starts from the set, from the whose distance you want to know, and then from there on it propagates towards the interior of the domain. And I think the algorithms are equivalent, apart from the fact that the velocity of the propagating sets is different. I think for standard Dijkstra or for for fast marching, the velocity is a constant, is basically constant. The velocity of the level sets, which propagate from the set. Whereas in my case with the gradient flow, this velocity is not constant. It's very quick in the beginning if you leave this constraint set, and then it slows down a little bit. So I think this is the main difference. And then computationally, of course, it depends on how you solve your problem. So in my case, we have to solve this gradient flow. And if you solve it naively, then you don't win anything, because you keep updating regions of your graph where the propagating front has not arrived to. So you keep updating those unnecessary regions. But if you solve it in a clever way, then probably it's equivalent to what fast marching or Dijkstra does. Yeah, but I mean, the main benefit is clearly that you can apply it to any situation where you have something like a gradient. It can be a graph, it can be the continuum, it can be a asymmetric graph as well. So it's very general. And yeah, Tim, do you want to reply to the second question?
Yeah, for the second question, so actually in the paper by Jeff Calder, there was proposed a method how to make Lipschitz learning sensitive to the distribution. But of course, this is in the infinity Laplacian sense. And to be honest, I haven't found a way to formulate this in a variational sense, because I have to, the underlying structure that I'm looking at is this variational problems. And in most of the formulations, if you look at it for finite p and the energies, and you send p to infinity, then the density always vanishes because it has no dependence on p. So I'm not, to be honest, I'm not sure how to do this in a variational sense. Make it sensitive to the density.
Right. So I mean, I guess one could potentially, but I mean, I don't like this solution. Like, for example, one could just multiply the, in other words, like directly like multiply by the density estimator. I guess this would be like in very naive way. But I guess like what is nice or just interesting from what happens when p is less than infinity is that directly from the fact that the points are distributed according to, you know, some distribution, that this already makes the density emerge in the limit.
Yeah.
That doesn't have to force anything. But okay, maybe it's just the way it is for p equals infinity. I don't know. But I mean, you mentioned that Jeff has a way to deal with this. Maybe, I mean, but okay, we can speak in the
Yeah. I mean, what I did was what you said, Nicholas, is that I multiply it by rho of x times rho of y on the weights, just using the kernel density estimator. So it was the naive way of doing things. So let's move to the breakout room then for further discussion. So so if you can push us there, Catherine.